Okay, I think we should get started. So hello, everyone. Thank you for joining us. I hope you are all doing well. I hope everyone is safe and healthy. So welcome to the AIP Open Seminar. And today is the turn of the Functional Analytic Unit to present our research. So before we start, I would like to remind you some of the rules of the AIP Open Seminar series. So number one, please note that reproduction is not allowed. Number two, please note that reproducing any part of the contents is not allowed without the author's permission. Number three, the seminar will be recorded and the video will be made publicly available on our center's website. And number four, if you have any questions or comments, please click the Q&A tab. You can also put the questions in the chat box. Okay. And we have a series of seminars which are open to everybody. So please go to the AIP Open Seminar Series website to see the list of the seminars available. So every week we have a seminar at the same hour on Wednesday at 3 p.m. on Wednesday. So next, so this is like the last seminar of January. Next month we have a series of seminars starting from February the 3rd with the knowledge acquisition team, and then going on to the computational brain dynamics team and language information access technology, continuous optimization, and tourism information analysis team, and approximate Bayesian inference team. So this is like February and March. So please come back and join us. I will start a little bit. I will talk a little bit our team. So our unit is called the Functional Analytic Learning Unit at the Weekend Center for Advanced Intelligence Projects in Tokyo. So we are a pretty small unit at the moment. We have 3 members. So there's me, there's Ming at the top, and we have Giancarlo Buella, and we have Wang Nguyen. So the methodologies of the main purposes of our unit is the development of machine learning and statistical methodologies using functional analytic methods. That's the name of the unit. It's called Functional Analytic Unit. And we particular focus on the Hilbert space methods, and one particular focus is reproducing kernel Hilbert spaces, RKHS, both in the scalar value and vector value setting, matrix and operator theory, Riemannian geometry, and optimal transport information geometry. And we tend to work on these fields in the direction of, in connection with Hilbert space methodologies, functional analysis methodologies. Now our main focus is on kind of the methodologies, but we are also hoping to working on applications as well. So the targeted applications are functional data analysis and computer vision, brain imaging, image and signal processing, brain computer physics, etc. So the applications are these are some of the applications that we are targeting, and we are always looking for collaborations and for new members as well. So this is a schedule of today's seminars. We have 3 talks. So the first one will be by me on the geometry of Gaussian measures, covariance operators, and Gaussian processes, from information geometry to optimal transport. Then Giancarlo will talk about characteristic kernels or matrix spaces in negative type, and Wang Nguyen will be talking about functions and graph with low-vast vectors. So this is the schedule. And now I will start. Okay, so this is my talk. So my talk, the title of the talk, the geometry of Gaussian measures, covariance operators and Gaussian processes, from information geometry to optimal transport. So the purpose of the talk is I'm going to present an overview of the generalization of the geometric structures for Gaussian measures on Rn, including the following: Riemannian distances, divergences, optimal transport distances, and along with the connections and unifying formulations to an infinite dimensional setting of Gaussian measures on Hilbert space, Gaussian processes, especially in the RKHS setting. So my focus is really on the infinite dimensional setting, and the finite dimensional setting is really kind of an overview of previous work. So what is the motivation for the study of geometric structures of Gaussian measures and covariance matrices? Now, these Gaussian measures and covariance matrices they play a very central role in probability statistics, and they have been studied a lot. But they also have a lot of practical applications as well. We have applications in brain imaging. We have many applications in computer vision, in radio signal processing, in brain computer interfaces, and so on. So there actually have been a very large number of work on these applications using Gaussian measures and covariance matrices. And so the geometric structures play a very important role in these applications. So I will talk about, there are three things that we'll be talking about. We're talking about Riemannian distances. So I will talk about the Fisher-Rao metric and like find very Riemannian distance, and we'll talk about the Log-Determinant metric and reviewing them. And then I will talk about the infinite dimensional generalizations of these two covariance operators, and I will talk about the RKHS setting. For divergences, I will be talking about one particular type of divergences. It's called the Log-Determinant divergences, both in the finite and in the infinite dimensional setting. Then I probably will spend more time talking about the optimal transport distances, the exact two versus time, and one particular type of transport distances, the exact two versus time distance in the Gaussian setting, and the entropic two versus time distance in the Singhorn divergences. I wouldn't talk about these divergences, the distance and divergences in the Gaussian setting, both in the finite and the infinite dimensional setting. So the optimal transport distances that I will be talking about, especially in the entropic setting, I worked in quite recently. So I probably wouldn't spend a little bit more time on talking about them. So now, I will be focusing, at first I will be focusing on zero mean Gaussian measures so that we can forget about the mean. And so in this case, the distance and divergences between zero mean Gaussian measures basically correspond to, so we have a one-to-one correspondence between Gaussian measures and the zero mean Gaussian measures and the covariance matrices operators. So the geometric structures, distances and divergences between zero mean Gaussian measures correspond to the distances and divergences between covariance matrices and covariance operators. So now, why do we care about like, the kind of the Riemann distances and all the divergences and so on? So at first, we always have the Euclidean metric. So we want to compare like two covariance matrices A and B. Then we can always use the Euclidean distance, which is a Frobenius distance between A and B. This is very easy to implement. It's very fast to compute. But the drawback of these distances is actually the Euclidean distance is actually matrices just as vectors, and so it doesn't really take into account any of the structures of the matrices, and so it's not. It tends to be suboptimal in various practical applications, and this is the reason why people have been working on various other non-Euclidean distances. So I will start first, very briefly. This is a classical topic on the Fisher-Rao metric. The affine invariant Riemannian metric for the zero mean Gaussian length. These are the so the set of zero mean Gaussian lengths are uniquely characterized by the covariance matrices. So we can have an identification of the set of all zero mean Gaussian densities on Rn with the set of all SPD matrices of the size n by m. So now this is the set of all zero mean Gaussian densities on Rn can be parameterized. So it's because it's characterized by uniquely by the covariance matrix. So the covariance matrix can be parameterized using parameter theta. And since it's a symmetric matrix, so we can characterize it by its upper half, which is just n times n plus 1 over 2 elements. You can use like n times n plus 1 over 2 parameters. And so we can consider this as a smooth manifold. And on this manifold, we can define a Riemannian metric, which is given by this formula of Ti, formula 2 here, Ti j theta here. And this can be shown to be, this is something we call the Fisher information matrix. And in this setting, we can show that it's positive definite. So it defines the Riemannian metric on this manifold as it's called the Fisher-Rao metric or the Fisher information metric. So this this Fisher-Rao metric or Fisher information metric is a central element in information geometry, and Japan is a powerhouse in information geometry. It was led by Professor Amari at Brigham. So there has been a lot of work done by Japanese researchers on information geometry. So now it's done in a very general setting. Now in the we are here within the Gaussian setting, so it's very nice because we can actually work out the explicit expression for the Fisher-Rao metric is given by formula 3 here. And then we make the identification of the the set of Gaussian method for the set of symmetric positive definite matrices, then it is basically a half of something we call the affine invariant Riemann matrix on the set of simplicities n here. It's given by equation 4. So it can be computed explicitly. So this affine invariant Riemann metric has been studied for a very long time in mathematics. So I'm just kind of listing some kind of very recent references, recent references here, but it has been studied for a very long time. And it's actually very nice because we have between the two matrices A and B, there's the unique geodesic joining them. It's given by this equation 5 here. It has a closed form, and then the geodesic distance also has a closed form given by this equation 6 here. So it's like the Fisher-Rao distance between zero mean Gaussian meshes on Rn. So everything is going to be computed explicitly here. It has been used a lot. And so one other popular use distance is something from the log-Determinant metric, and it's motivated in the setting of diffusion tensor imaging. And so in this case, it's simpler than the affine invariant Riemann metric. And there's also a unique geodesic joining any two matrices A and B. So it's given by these equations 7 here. And we have, and so the Riemann geodesic distance also has a closed form formula, and it's simpler than the affine invariant Riemann distance. It's given by this equation 8 here, and it's faster to compute. And moreover, with the Log-Determinant metric, we can actually define an inner product structure, a vector space, and an inner product space structure on the set of SPD matrices. So we can define positive definite kernels on this set. And for one example, is that we can define Gaussian kernels, for example. So how can this be used? One very common pipeline here is the founded kernel methods with the Log-Determinant matrix. So we can define kernel methods on covariance matrices. This is an example from computer vision, but the pipeline is very common for the other applications as well. So this is image classification by covariance matrix representation. So suppose we want to classify images, we can one way to do it, for example, is to represent each image. So we extract the features from the images, and then for each image we extract its features, and then we compute the covariance matrix of the features. So each image is represented by a covariance matrix. And so now we can compute the distance. We can, if we want to do classification, we can compute the distance, and then we can compute the Log-Determinant distance. And since we can define positive definite kernel on this, using the Log-Determinant distance, we can define a kernel on top of it, the Gaussian kernel, for example. And then we can do classification using kernel methods like SVM. So this is one way that we can apply. This actually has been applied in computer vision, and it has been, this pipeline is common in various applications that we were talking about as well. So this has been applied. What we are going to do now is we are going to move from the covariance matrices to covariance operators, because before we were kind of comparing covariance matrices. We do classification, we can do clustering, we can do regression, etc. So now we want to do it more. We want to move on to set up from covariance matrices to covariance operators. I will talk later on about how actually it can be used also for in computer vision. But now let's talk a little bit about the mathematical formulation first. So suppose now we have an infinite dimensional Hilbert space, and we have an A is an operator compact self-adjoint and strictly positive compact operator on H, even if H is an infinite dimensional Hilbert space. And here, so A is, for example, is the covariance operator. So the problem, so it's this the infinite dimensional formulation is going to be. So I wanted to generalize. We want to generalize this Log-Determinant distance and the affine invariant Riemann distance to the infinite dimensional setting. Now the infinite dimensional thing is actually substantially harder to do, because now this covariance operator A, for example, has an infinitely many eigenvalues. And the eigenvalues are always greater than or equal to 0, but they go to 0 as lambda k go to 0 as k goes to infinity. So the problem with that is actually 1 over lambda k goes to infinity, and log of lambda k goes to negative infinity. So if we take the inverse, for the affine invariant Riemann distance, we have to take the inverse. It goes to it's unbounded. And also if you want to compute the log, for example, the log is unbounded. So the expressions that we gave before will not be well defined. So the approach, So there was an approach to generalize the affine invariant Riemann distance proposed by Larotonda in 2007. So now we have to consider this set of Hilbert-Schmidt operators, because the covariance operators are also Hilbert-Schmidt operators. The set of all operator with the finite Hilbert-Schmidt norm, and for if I self-adjoint the norm square, the Hilbert-Schmidt norm square is a summation of all the eigenvalues square. And so Larotonda considered the set of extended Hilbert-Schmidt operators. So the set given by equation 10 here of the form A plus gamma I. So instead of just A, we have a set of A plus gamma I, where I is the identity operator. And then he considered the set of all A plus gamma I, which is greater than 0. The self-adjoint A plus gamma I is greater than 0. So then if we do this, then A plus gamma I is inverse is bounded, and log of A plus gamma I is also bounded. So these two operations are well defined. So it's simpler for me to talk about the log Euclidean distance, the generalization of the log Euclidean distance, which equal the log Hilbert-Schmidt distance, using the concept just described. So I want to generalize this log A minus log B, the norm, the distance of the log A minus log B from modulus F to the infinite dimensional settings. So we want to have the distance between A plus gamma I plus and B plus mu I. So it's given by this formula. So we use this A plus gamma I before. So we have log of A plus gamma I, this is bounded, and log of B plus mu I, which is bounded. Now this is not enough, because it's not enough to use the Hilbert-Schmidt norm for this object. We actually have to use something called the Hilbert-Schmidt, extended Hilbert-Schmidt norm. Is given by this equation 12 here. So the norm of A plus gamma I square HSX is equal to the Hilbert-Schmidt norm square of A plus gamma square. Now, the reason we have to do this is the identity operator has the Hilbert-Schmidt norm of the identity operator is infinite. And so if we just use the Hilbert-Schmidt norm for this object here on equation 11 for this distance invariant, just if we remove this x here, then we will have generally infinity. So that's why we define this extended. This is the idea of the extended Hilbert-Schmidt norms. And so we set the norm of the identity operator to be 1. This is a form of compactification, a form of regularization. And this corresponds to an extended Hilbert-Schmidt inner product is defined so that the identity operator is orthogonal to all the Hilbert-Schmidt operators. So if we use this extended Hilbert-Schmidt operator, A plus gamma and B plus mu I plus the extended Hilbert-Schmidt norm, then everything here is well defined. And we can also have, we can define, there's also a Hilbert space structure as well. And we can also define like a kernel using this distance. So in Larotonda is concerned more with the affine invariant Riemannian distance. So then with the construction before, we can also define the Riemannian metric as in equation 14 and the Riemannian distance as in equation 15 here. So it has very similar form to the finite dimensional case, except that we use the extended Hilbert-Schmidt operators and the extended Hilbert-Schmidt norm. So the kind of these formulas are kind of abstract because these are infinite dimensional operators. So the formulas are fine, are very concrete and have a closed form, but they are infinite dimensional operators. So either in practice, either we have to do a finite dimensional approximation, or in the case of reproducing Hilbert spaces, we can have Gaussian formulas in terms of grammar matrices that we can compute. So let me talk about this RKHS setting where we have Gaussian formulas in grammar matrices where we can compute everything in a very concrete way and we can apply it immediately in practice. So let's talk about reproducing kernel Hilbert spaces and covariance operators in RKHS and covariance operators in RKHS. So the motivation, this one is actually from computer vision, but it's also similar in other fields as well. So the covariance matrix system can encode linear correlations of input features. And so by defining a kernel, we can have a form of non-linearization. So we can map original input features into a high or generally infinite dimensional feature space. And then we can define the covariance operators, which are the covariance matrices infinite dimensional features. And so these will encode the nonlinear correlations of input features and just provide a richer and more expressive representation of the data. So suppose we have a possibly affinitive kernel K on matrix space X, say, and an RKHS HK. Then we have a feature map phi, which map phi x, map x to HK, so phi h equal to px. So that phi x, the product of phi x and phi h is equal to pxy. This is something we call the canonical feature map in machine learning. And suppose that we have the 16 here, suppose that the norm square of Vx, which is equal to just equal to Vx less than infinity. Then we can define an RKHS mean vector. It's just by this equation 17 here, it's just the mean of the feature Vx with respect to the rho, where rho is a probability distribution on X. And we can also define RKHS covariance operator. So it's just a covariance operator of the feature given by this equation 18 here of the feature Vx. So now, what the empirical, if we are given a set of m data points from X, then we can form informally this feature map V here will give an infinite feature matrix A in HK, and so it has like an equation 19 here. So Vx has a Vx1 up to Vxm, so kind of this set. Informally, it can be considered as a data matrix in infinite dimension. But formally, it can be it's about a linear operator. But we can just like where you can just think about it as an infinite feature matrix Vx in equation 19 here. So then with this, we can also so using this feature matrix Vx, we can compute the empirical mean as well. It has an empirical mean, just a mean of all the Vxi. And so this is the empirical just mean of mu of Vx is in equation 21 here. Which is the empirical version of mu phi. And in particular, in the case when the kernel is linear on RD, then we just have like this is a summation of xi, just the sample mean in Euclidean space. So that's the case when we have a linear kernel. Otherwise, so it's a kind of a nonlinear generalization of the sample mean in Euclidean space. And the same for the covariance operator. We can define the covariance operator of the feature matrix Vx. We can define this. So it's given by this equation 23 here. And so it's the empirical version of the theoretical covariance operator in equation 22. And in the case when the kernel is in the case when the kernel is a linear kernel on RD, then we just get a Cx just equal to the sample covariance matrix in RD, just as the standard sample covariance matrix. So now this actually has this representation has been used in computer vision. It's a form of nonlinear generalization of the covariance matrix representation of the images we talked about just before. And so in this case, we can represent an image by a covariance operators. So we can extract data matrix features from the image, and then we can apply a kernel. And then we can represent the image by this CVX here. Now, CVX here is actually an infinite, it's an infinite dimensional operator. It has finite length, but it's actually an infinite dimensional operator. So the representation is actually implicit because phi here is generally implicit. Now the computation are carried out via gram matrices. So it has been here are some of the examples of the work using this. For example, in Tehran in CVBA 2014, I was kind of involved in some of this, and then we have kind of some recent work in optimal transport actually in Feynman 2019. So now if we have this representation of using first an image using an operator, covariance operator CVX, and we can if you want to do classification, for example, then we have to compute the distances between them. So so this is an example. We can compute the log-linear distance between them. So this the log-linear distance would have a closed form formula in terms of the gram matrices. The formulas in the next couple of slides are very complicated. I'm just going to show them to show you that there is a closed form formula, but you don't have to worry about them so much. So this is a case when the dimension of HK is infinity. It's the case of the Gaussian kernel. So this is the formula, but I'm just showing you to show that that's the closed form expression. So now what we can do, so this can be applied in practice, has been applied in some classical computer vision. And so this one is an example for image classification. It's like a two-layer kernel machine. So we can represent, as before, we can represent images. We can extract the features of the image, and we can apply a kernel on these features. So then we can represent each image by a covariance operator. Now, if you can compute, we can compute the log-Hilbert distance between this covariance operator. So since this is a Hilbert this is the Hilbert distance, we can apply Gaussian kernels, many possible affinity kernels, 25 many possible affinity kernels such as Gaussian kernels. So we can apply another kernel on top of it on the log-Hilbert distance. So we have, and then we can apply any kernel. So this is a two-layer kernel machine. I remember before that we have the log Euclidean distance. We don't have this layer of kernel K1 here. We just apply we just have compute the log Euclidean distance, and we can apply the Gaussian kernel, for example. In this case, we have two layers, the two-layer kernel machine. So, and then there have been also various work to make this faster, to make this computation faster by doing approximation as well. So there have been some work on that, along that line. So I'm going to give you a very simple example to show you that this is not an abstract formulation. It has to be, it can be applied, practice has been applied. This is an example of object recognition. It's actually a very simple example, nothing fancy, kind of a setup, data set with some classes of objects, like we have tomatoes and apples and some toys here, and then we can extract some of the features here, like the location, the intensity, and the absolute value of the magnitude of the gradient here. And so this is like the example obtained using classification using the approach that I have talked about just now. So the first line is the Euclidean distance. So here, in this case, actually we represent the image by covariance matrices, and we just apply the Euclidean distance. And then we apply the next one. It actually has to do with the log-determinant divergence I will talk about next. And the next line is the log Euclidean distance. So in this case, we kind of exploit the non-Euclidean structure of the covariance matrices, so it has much better performance. And the next two lines are the Hilbert-Schmidt distance and the approximate log Hilbert-Schmidt distance. So you can see actually there's a very big jump between the log Hilbert-Schmidt distance and the log Euclidean and the Euclidean distance, because we actually, number one, we use a form of nonlinear generalization of the features, and number two, we exploit the non-Euclidean structure of the geometrical structures of the covariance operators. So this is an example where it can be concretely applied, because everything that we talk about have a closed form and can be, have a closed mathematical form and can be computed efficiently. Okay, so now that was the Riemannian distances. These are almost some of the distances. I was just talking about some of the distances. Actually, there are other distances as well. So now I will talk about the divergences. I will talk about, in particular, I will talk about the log-determinant divergences. So this comes from the convex point of the set of SPD matrices. So before we have the Riemannian distances, they come from the view of the set of SPD matrices as a Riemannian manifold. Now we talk about the convex viewpoint of the set of SPD matrices. So this family is something we call the alpha log-determinant divergences, and so they are not, in general, they are not metric. They are not symmetric. It depends on the parameter alpha. So this setting here is, this family here is only symmetric when alpha is equal to 0, otherwise not symmetric. Now, so they correspond to the Roni and Kuhn-Beck-Lapierre divergences between 0 mean Gaussian measures on Rn. In the case when alpha is equal to 1, correspond to the Kuhn-Beck-Lapierre divergences. So it's not sort of symmetric, but they are fast to compute. Now I would like to generalize it as before. So these divergences have also been applied or various applications as well. And so what I would like to do is I would like to generalize this to the infinite dimensional setting as well. So to do with this, instead of the generalizing for the instead of using the Hilbert-Schmidt operators, I will talk about something called the just class operators. So covariance operators are just class operators, and briefly what it means actually, they have infinitely many eigenvalues, and the just class norm will be equal to some of the absolute value of all the eigenvalues, and the choice will be the sum of all the eigenvalues. So something here we have infinitely many eigenvalues. And so let's talk about the log-det, for example. So the log-det of A, for example, is equal to choice of log of A, so it is summation of all the log of lambda k. Now, because we have infinitely many of these eigenvalues and they go to 0, so the log of lambda k will go to infinity, negative infinity. So the summation is actually negative infinity. So it's actually, so this expression, like all the log-det here, will not be well defined. So what we need to do is actually we need to extend the set of operators, the set of just class operators A, and the set of the function choice and the determinant function as well. So similar to the idea of the extended Hilbert-Schmidt operators and extended Hilbert-Schmidt norm, we introduce something in this setting here, something called the extended choice class operators. So we have A plus gamma I. Now the problem is actually the standard choice definition of I is infinity because all the eigenvalues equal to 1. So we have infinity. So what we need to have is something called the extended trace. So just of A plus gamma I with the trace of A plus gamma I. So then we set the extended trace of the identity operator to be 1 instead of infinity. So as before, it's a form of compactification. And then we have to employ an infinite determinant. And we have this classical Fredholm determinant here, just determinant of A plus gamma I plus I just go to the product of all the 1 plus lambda k from 1 to infinity. So this one is only holds when gamma is equal to 1. So we need to extend this to 29 here, something called the extended Fredholm determinant. So this one is well defined for any gamma here. And so this is a simplified version. So by using this, we can generalize the alpha log determinant divergence before, and we have something called the alpha log determinant infinite dimensional alpha log determinant divergences. And so this one is a simplified version. Actually, it looks very similar, but then A and B can be not just classical, and it's always well defined, and it has closed form formulas in RKHS setting. And there's also related work. So I mentioned that actually there has been related work in the RKHS setting before with the work of Don and Chalapa and also Harandi and ONC 2014. But this formulation mathematically are valid in the finite dimensional setting. So what does it really mean? Now, what does it really mean? What does it really mean when we are comparing these operators, A plus gamma and P squared gamma? What is the role of gamma? What does it mean, like probabilistically? What does it mean? So in the finite dimensional setting, we know that the alpha log determinant divergences correspond to the linear divergence and the Quebec level divergences. So this can be shown also here. So this is the meaning of I would explain the meaning of this when gamma go to 0. So on RD, when two Gaussian densities are always equivalent, so that they have the same support. Now the situation is very different in infinite dimensional setting. There's a classical theorem by Feynman and Hayek says that in the infinite dimension, I think two Gaussian measures are either equivalent or they are mutually singular, so they can have disjoint support. So in which case the K divergence is equal to infinity. So what we can show is actually when alpha, this is an example when alpha is equal to 1. So when gamma go to 0, then the Log-Determinant divergence between C plus gamma and C0 plus gamma I is equal to twice the K divergence between the two Gaussian measures with the same mean with the covariance operator C and C0. So that is this gives a probabilistic interpretation of the divergence we talk about when we set gamma to go to 0. So this setting can be generalized in a very general way. It can be generalized in a general way to have families which is become the alpha beta log-determinant divergences. It encompasses both the alpha log-determinant divergences and the phi invariant Riemannian distance. So it can be done in a very general way, and these all induce the phi invariant Riemannian metric. So they all induce a Riemannian metric on the set of positive definite operators, and they all have closed form formulas in the RKHS setting. So okay, so that was like the Riemannian distance and the divergence. And now we're going to talk about the optimal transport. Okay, if we have enough time, maybe I'm covering too much material. So optimal transport is now a very important topic in machine learning. There's has been a lot of work recently. So very briefly, the optimal transport. I'm going to talk about I'm just briefly reviewing the definition of optimal transport system between the probability measures nu0 and nu1 on a metric space X. Let's say X equal to Rn. Post function cxy. So it's given by this optimization problem here in 32 here. And when the cost function cxy is a distance function of the metric space, then to the power p, then we have something we call the p versus time distance. So the p root of this distance is a metric on the set of probability measures with finite p moments. So this is a very huge topic in mathematics. There's a lot of references, but there are one can have a look at, if you're not familiar, one can have a look at the books by Villani here. They're very comprehensive. And so now in the case, we were just talking about the Gaussian case here. So in the Gaussian case, thankfully, in general, of course, in general, it's very hard to solve this optimization problem. But in the Gaussian case, we actually have closed form formulas. So let's talk about the case when we have two Gaussian measures. Here, so we have a closed form formula given by this equation 35 here. So it's given by in terms of the two norm here. So we just have the mean square, the difference of the means, and then we have the trace term here. So when the mean are the same, we obtain something called the Bruce versus time distance between the SPD matrices. So it's given by this so 35 and then right next to 5. So this also, if so in terms of the optimal transform problem, it also has a Riemann in the metric interpretation. So we don't have to worry about this equation. You just say that it's actually a Riemannian distance, and on equation 38 here we have a geodesic. So it also has a closed form. For the Riemannian metric on 36 and 37 is not as explicit as the other case, but we also has I'm just saying that this actually is also a Riemannian metric. So what is nice about this Bruce versus time distance is actually it's also valid in the case with AB and singular. So remember that in the other cases of the Riemannian distances and the log-determinant divergences of the A and B all have to be strictly positive definite. But in this case, they can also be singular because we are just taking the trace. And so in the setting up quantum information theory, where the trace of A and B is equal to 1, we obtain something we call the Bruce distance. So now, so why do people talk about entropic work on entropic regularization? See, the exact optimal transport distances in general, not just analytically challenging, also computationally demanding, and they also have a pretty bad sample complexity. So that is the motivation for the entropic regularization approach. So instead of just minimizing the expected value of the post C, we also add a term epsilon, KL, gamma with respect to the product measure of mu and nu. So this is like the mutual information of gamma with respect to mu and nu. And so this was done by Couture in 2013. So it actually is equivalent to the classical string gauge problem from a long time ago, 1931. So this can be solved efficiently using something we call the synchron algorithm. And so now I'm just going to talk about, okay, sorry. So in general, this kind of introduced the bias because actually this this entropic OD here between mu and mu is actually not equal to 0. So it's either distance or divergence. So so researchers introduced the synchron divergence. We kind of subtract this bias, so that it becomes a divergence. There has been a lot of work recently along this line. There are also many applications as well. So now let's talk about the Gaussian setting, because this is a setting where we can actually obtain a closed form formula and see how they look like. So there has been so this actually this closed form formula actually appeared very recently, like last year. So there were 3 papers that appear kind of almost like simultaneously, kind of around the same time. So the formula we can solve for this by using the fact that using something we call the maximum entropy property of the Gaussian densities in Rn. So basically, this KL of mu x with respect to mu x and mu y is just a mutual information of mu x of the mu x and mu y. So it's given by hx plus h5 minus h of xy, where h here is the differential entropy. And we have something we call the maximum entropy property of Gaussian density. So mu x has mean 0 and covariance matrix C, and then the entropy is maximum if and only if x is the Gaussian measure. And so if x is my Gaussian measure, then the mutual information is minimum if and only the choice density is Gaussian. So with this property, when we solve these optimizations here, the first term depends only on the mean and the covariance. And so the last term is minimum if only if it's the choice measure is Gaussian. And so the minimizer has to be a Gaussian density. So it has to have a particular form that's given by this equation from here. And so the covariance operator the covariance matrix has to have a block form like this. We see here is a cross covariance matrix. And we can compute the KL divergence as well, that is mutual information as well. So it also has a closed form. So now we can plug everything in here and we can solve for this optimization problem and we can get an answer. This is one way to do it. There's another way I will talk about later on. And so when we solve this optimization problem, we obtain these formulas here. So this is the entropic distance OD, and then we obtain the synchron divergence. So we have nice and closed form formula. So these are formulas that were obtained by the papers that I talked about before. And the unique minimizer gamma, of course, is the choice Gaussian measure. Now, if you look at formula 42 here, there's a dimension D here. Now, if you look at if we look at this, we might think that when D goes to infinity, this is not well defined. This is not true. Actually, these formulas are all valid in the infinite dimensional setting, which I will talk about next. Now, so in the infinite dimensional setting, the 2 versus time distance is also well defined. It has the same form as the finite dimensional setting, and it's also well defined when I'm sorry, it should be C0 and C1 when the covariance operators are singular. This is actually a big advantage compared to the compared to the other distances. For example, like for the other remaining the remaining distances or the Log-Determinant divergences, well, we have to use a form of regularization to define the distances. In this case, the distances is already well defined without any form of regularization. But nevertheless, the entropic regularization does give you some very nice theoretical properties. Okay, so this is actually the things that I actually completed like not so long ago. It's a very recent work actually. So now, let's go on to the infinite dimensional setting now. Now the problem with the infinite dimensional setting is actually the finite dimensional methods are no longer applicable. So first, let's look at the entropy here. Now this entropy here, as before we talked about, because it does not generalize to the infinite dimensional setting because we have an infinite determinant here. We have to multiply infinite eigenvalues, and we have this d goes to infinity here. So this is actually not well defined. And for two Gaussian measures and the joint Gaussian measure gamma, it also has like so the covariance also has this form. We see here is a covariance, the cross covariance operator now, but it has the same form as before. But when we compute this mutual information here, now the right-hand side is no longer well defined. This equation 45 here, because it's the log that is always in negative infinity. So this is actually not the right-hand side is not well defined, but the left-hand side is actually well defined. Can be infinite, but it's well defined. So we have to generalize this maximum entropy of Gaussian densities. Now, so for a general gamma joint measure here, the mutual information is always well defined. It can be infinite. In which case we do not care about it because we are doing a minimization. So we only care about in the case when it's finite. So now we can show that this quantity here is always, so the KR between gamma and the product mu0 and mu1 is minimum if and only if gamma is equal to a Gaussian, the joint Gaussian measure. And so the joint Gaussian measure have minimum mutual information. So the generalization of the maximum entropy property is a minimum mutual information. So so this theorem is just don't worry about this. It just says that it's just a formula. That's what I said before. The joint measure has its minimum if it is a Gaussian, a joint Gaussian measure, and it has an explicit form. So we can use it in the minimization problem. So consider this problem two stars here. So it has to have so the minimizer has to be a Gaussian as before, a Gaussian measure as before, and then we can solve for it. We can directly solve for solve it by this direct method. This is of the infinite dimension optimization problem here. But this can be solved. This can be solved, and we can obtain for this V here, we can obtain a V, and we can obtain a solution. And another method is we can solve it by because it's connected to the Schrodinger bridge problem. So we can actually solve using something called the Schrodinger equation here. So this one we solve for the random nuclear density of gamma with respect to the product measure mu0 and mu1. So then we can solve it, and we can also obtain the the explicit answer as well. So this is the optimal transport plan. So it actually has the same form. Basically, in the finite dimension, I think there is the same as before. But this, here the operators are infinite dimensional operators. So it has the closed form. It has to be a Gaussian measure, and everything is well defined. So this is the distance, the entropic distance. The only difference with the finite dimensional distance is actually in this case the log that here is the that here is a log is the threshold determinant, and we can also then we can have the one property of this entropic distance is actually it's if we have two measures, two general probability measures with the same mean covariance of the C0 is 1 and the entropic distance is minimum if you only the measures are Gaussian. So this is one nice property also of the Gaussian measures as well. And then we can also solve for the synchron divergence, kind of the closed form formula for the synchron divergence. So it is a semi-metric on the set of Gaussian measures. So it's always symmetric, so we're greater than or equal to 0, and it's equal to 0 if the two measures are the same. So now the limiting case is so when gamma goes to 0, we obtain the single divergence will go to the single with the 2 versus time distance, the square of the 2 versus time distance, and when time goes to infinity, we just have the MMD, the maximum mean discrepancy. So it's an interpolation between the it's an explicit form of interpolation between the maximum mean discrepancy and the 2 versus time distance. Now it's connected to the Gaussian processes as well, because we have a one-to-one correspondence between the Gaussian processes and Gaussian measures. So if you have the Gaussian processes with the mean is finite and with the m squared mean the mean becomes to be okay. So if T is a complex set in RD and the mean function belongs to L2 of T, and then we have this the covariance function satisfy KTT integral of KTT dt less than infinity. That is a one-to-one correspondence with the Gaussian process with mean m and covariance of function k, and the Gaussian measures on L2 t with mean m and covariance operator ck, where ck is just the integral operator defined by the covariance function kst. So now since we have this one-to-one correspondence, we can define, given any distance or divergence between Gaussian measures, we can define distance and divergence, the corresponding distance and divergence function between Gaussian processes as well. So we can have like a geometry of Gaussian processes by the geometric structures of Gaussian measures. So the one nice properties of this income divergence is actually differentiability is always differentiable. It's always differentiable in finite dimensional setting. It's always differentiable, and also in the infinite dimensional setting, it's always differentiable when X is positive and just class operator. This is not the case for the versus time distance. In the infinite dimensional setting, the versus time distance is not differentiable. And also the single divergence is strictly convex. So it has a close, so it has so the consequence of the differentiability and the strict convexity is actually the single, if we solve for the barycenter of a set of Gaussian measures using the single divergence, and there's always a unique solution. So this, so there's always a unique solution, which is a Gaussian measure. It's given by where the covariance operator is given by this equation. It always has a unique solution. We can solve it using an iterative procedure. And this equation is actually better than it's better behaved than the equation of the exact versus time distance, because so it's unique. It always has solution at in both the singular and non-singular setting. Because the equation number 57 here, 51, 57. Equation 51 is not well defined in the case when it's not suitable for finding the barycenter when the barycenter is singular. Now in the RKHS setting, if we have two Gaussian two probability measures rho1 and rho2, then they correspond to two Gaussian measures defined by the mean by the mu phi of rho1 and by the with mean mu phi of rho1 and with mu phi of rho I, and then c phi of rho I is a covariance operator. So we have two Gaussian measures in RKHS induced by these two probability measures rho1 and rho2. So we can define a single divergence with them as well, which is well defined and has a closed form formula. And so if we have a characteristic kernel, then this will define a semi-metric on the set of probability measures, variant probability measures on X. So this has the closed form formula, those are the gram matrices. Okay. Now, and in the case when epsilon goes to infinity, then we obtain the kernel MMD divergence. And in the case when epsilon goes to 0, we obtain the kernel versus time distance. So it's an interpolation between the kernel versus time distance and the MMD. So okay, so the convergence. So for the versus time distance, if we have a set of Gaussian measures, then the convergence in versus time distance is equivalent to the weak convergence, and it's equivalent to the convergence of mean and the covariance operators in the trace norm. And in particular, in the finite dimensional setting, there also converges in the Hilbert norm as well, but this only happens in finite dimension with an extra factor of d here. Now, the single divergence actually has nicer convergence properties because it converges in the Hilbert norm. So, in particular, the convergence in the versus time distance will imply convergence in the synchron divergence, but not vice versa. So the nice thing about this Hilbert-Schmidt norm convergence is that we can apply laws of large numbers for Hilbert space value random variables to obtain the explicit convergence rate. So this is the convergence. This is the convergence rate. Here, for the case of the kernel, is bounded. So this expression here, this convergence really is dimension independent, and with the case of Gaussian kernel from kappa is equal to 1, so it's actually completely dimension independent. This is the convergence rate of the empirical Gaussian measure groups and the theoretical RKHS Gaussian measure. And this is the case when the kernel is, in general, not necessarily bounded for some of the linear kernels, polynomial kernels. In this case, the bound is a little bit looser, but it's still dimension independent. But you don't have to worry about the theoretical details. That is, we just have the convergence. So in the linear kernel, then we obtain the convergence of the empirical Gaussian measures in the synchron divergence. So in this case, the kappa here is given explicitly in terms of the covariance operator and the mean, like the chase of the covariance operator, the Hilbert-Schmidt norm, the covariance operator and the mean. And it's also dimension independent, so it's hold for any Hilbert space. And so, so here we have this epsilon, so it's bigger when epsilon is small. So when epsilon goes to infinity, for example, this whole thing will just explode, so it wouldn't be vacuous. Now, for the versus time distance, we only have the convergence rate for the finite dimensional case. We do not have the convergence rate for the infinite dimensional case. So here it depends on the dimension d. So it's dimension dependent. So it's different from the synchron divergence. Okay. So now I'm going to give some example, a couple of examples here. So this is the distance and divergence between two empirical RKHS Gaussian measures. And the first one is x and y. On the left, x and y generated by the same mixture of Gaussian distributions. So on the top, and we use the Laplacian kernel. So on top, we have the versus time distance. And then we have the synchron divergence of epsilon equal to 0.01, and then 0.1, and then we have MND, which is correspond to epsilon equal to infinity. So now we can see that the versus time distance actually converges very, very slow. So it should converge to 0 because we have the same mixture, Gaussian mixture here, so it should go to 0. Now the versus time distance go to 0 very, very slowly, whereas the synchron divergence go to 0 faster, the bigger epsilon is. And on the right-hand side, we have data generated from two different Gaussian mixtures. So the limit is non-zero, and you can have the same behavior. We have the same behavior, and this is just the convergence of the synchron divergence between empirical Gaussian measures. Now I'm talking about this one is to illustrate the difference in the dimension. So on the left we have the dimension of 100. On the right we have dimension of 500. So this is also the synchron divergence and the versus time divergence between Gaussian measures. So you can see actually for the synchron divergence, which is on the bottom here, the convergence is dimension independent. So it has very similar behavior. The dimension is 100, the dimension is 500. Whereas for the versus time distance, you can clearly see the difference, the dependence on the dimension. Okay, so I just sorry, I haven't had time to actually do any cool applications yet, but some of the kind of synthetic example to illustrate the differences. So of course, there have been a lot of differences in divergences, and it's not always clear which one we should use in practice. So there have been a lot of work recently to kind of try to have a unifying formulation for this distance and divergences. So some of the work here, for example, the work power Euclidean distance that unify Euclidean and log-Euclidean distances, and I was talking about the alpha and beta log divergences. We also have something called the phi power phi matrix that unify the phi invariant and log-Euclidean matrix, and I have something called the alpha Procus's matrix that unify the resources phi and the Euclidean and log-Hilbert-Schmidt distances as well. So there's a lot of work ongoing. So maybe I have covered too much material, but I would like to summarize. So here I've been talking about the Riemannian distances of the log-determinant divergences, the entropic optimal transport distances between Gaussian measures in both the finite and the infinite dimensional setting and infinite dimensional setting. And we show that we actually have closed form formulas in all cases, and we have in the, especially in the RKHS thing, we have concrete formulas in gram matrices that can be applied immediately in practice. And so for the remaining distances that we talked about in the log-determinant divergences, so we actually have to use regularization just to define the distances in the infinite dimensional setting. Now, in the optimal transport distances, the case of optimal transport distances, we actually do not need to use regularization to define the distances and divergences. But nevertheless, the regularized version have a very nice theoretical properties compared to the exact divergences in terms of sample complexity, differentiability, and the well-behavedness of the various center problems. So, of course, we have to be applications of this future work. Okay, so that's it from me. So I would be, if there are any questions, I would be happy to answer. So if there are no questions, then we move on to the next talk by Giancarlo.
Okay, so my name is Giancarlo, and today I'll talk about characteristic kernels on metric spaces and just a moment. Okay. Today I'll talk about characteristic kernels on metric space of negative type. So, okay, the objective of my talk is to basically present several examples among a class of ISPD. By ISPD, I mean integrally strictly positive definite and characteristic kernels based on completely monotone functions, and also on CND, conditionally negative definite kernels. Also a class of energy distance kernels based on bursting functions and CND kernels. A class of ISPD and characteristic kernels on products of spaces, one of them being the Euclidean spaces, that generalize the Gaussian kernel, which are known as the generating class, and also a class of ISPD and characteristic kernels on real hyperbolic spaces. And my talk is based on these two articles. So first, I will talk about something about embedding probabilities on Hilbert spaces. First, I will just remind these basic definitions of a positive definite kernel, which I think everyone is familiar. My kernel is real valued because on my talk, all my kernels will be real valued. A definition that's not so common is that of a conditionally negative definite kernel, which I also assume that's real valued. The definition is very similar to the positive definite case, but the real scalars, they must satisfy a restriction. Their sum must be 0, and the sign of the double sum is the opposite. So positive definite kernels, as you may already know, are related to inner products on Hilbert spaces, being the most important example, the RKHS, the reproducing kernel Hilbert space of the positive definite kernel. Conditionally negative definite kernels are related to distance squares on Hilbert spaces. And because inner products on Hilbert spaces and distance square on the Hilbert spaces are intrinsically related, CND and PD kernels are also intrinsically related. Just to remind the definition of the RKHS, and from now on, all my kernels are continuous. And because of that, the RKHS related to this kernel is a subset of the continuous function. X for me is also a Hausdorff space, and the RKHS satisfies those properties. If you have then a continuous kernel, we can define the kernel mean embedding for some measures. They must be of finite variation, Borel, with respect to the topology, and Radon regular, which is this technical condition that is very common on the setting. But for instance, if X is a topology space like the Euclidean space, like a finite, like a separable Hilbert space, there is here the hyperbolic space of those spaces satisfies this property. And the measure and the kernel must satisfy this integrability condition. So the square root of the kernel on the diagonal is integrable. Then under those circumstances, there exists a vector on the RKHS, which we call the kernel mean embedding, that satisfies this equality for every function on the RKHS. Then if you think if your kernel is bounded, and by assuming that the kernel B is bound, that the kernel K is bounded, all measures with finite variation satisfies this property. So I can define the kernel B embedding for every measure with finite variation with this technical condition. We define that this kernel is integrally strictly positive definite, or just ISPD, if the linear operator from the space of measures to the RKHS is injective. Can equivalently say that this double integral, which we can prove that is the inner product of the kernel embedding of the measure mu with itself, is zero only when the measure is the zero measure. Weaker definition is of a characteristic kernel, which again case bounded, and if you pick the operator of the kernel embedding, is injective modeled on the whole space, only on the subspace of measures whose zeroth moment is zero, or equivalently, that again the double integral is zero when restricted to the fact that the measure has its zeroth moment is zero, then the measure must be the zero measure. So if you have a characteristic kernel, then you can define a metric on the space of probabilities that are satisfies are Borel and Radon regular. So you pick those two probabilities, you use the kernel embedding, so you define those two vectors related to the kernel embedding, and you analyze the distance between those two vectors and define this as the metric, as the distance between those two probabilities. This is what the maximum discrepancy computes. Well, as I've said before, in just a moment, because P and Q, I'm assuming there are probabilities, the measure P minus Q at the set X, it's equals to zero. That's why this makes sense. And as I said before, as conditionally negative definite kernels and positive definite kernels are intrinsically related, one of those relations is that a kernel gamma is in D if and only if this kernel K gamma is positive definite, which I'll use in a moment. We have this technical condition is about 3 conditions on a measure mu that are equivalent. If you have gamma, a conditionally negative definite kernel that's on the diagonal is bounded, which from now on, I assume that gamma has a bounded diagonal. So those three integration properties are equivalent. With that in mind, if you have a measure mu that satisfies any of those equivalences, whose zeroth moment is zero, the double integral with respect to the kernel minus gamma, which is well defined by this formula, by this property, is equal to the double integral over the kernel K gamma, which makes sense by the way we defined it in this property. And also we can apply the kernel embedding of the measure mu with respect to K gamma because of those 3 equivalent properties. So this double integral here is always a non-negative number. I forgot to mention that the set of measures that satisfies those 3 conditions are a vector space. And then we say that gamma is a CND characteristic kernel if this double integral is zero only when the measure mu is zero, of course, under the restriction that the measure mu has the zeroth moment being zero. And we can define a metric on the space of probabilities of, again, Radon regular, that satisfies any of those 3 equivalent conditions. That's why this gamma here. And the formula is basically the same one as the mu-d. That's why I use the same notation. I just replace it the double integral with respect to the positive definite kernel K with minus gamma. Just a remark, if gamma is CND characteristic, usually the kernel K gamma will not be characteristic because usually CND kernels are unbounded, so and then the kernel K gamma will be unbounded. And it's convenient to have those 2 definitions for the characteristic property because, for instance, the most important kernels exist are the radial kernels, and every PD radial kernel in Euclidean space is always bounded, while CND radial kernels are usually unbounded, but not so much unbounded. They are always of the order of x squared. So at the maximum, you demand that your probability has a finite second moment. A definition, we say that a metric space has negative type if the metric is a conditionally negative definite kernel, and it has a strong negative type if the metric is a CND characteristic kernel. Those definitions can be found in Lyon 2013. Some examples of characteristic, some examples of characteristic ISPD and CND characteristic kernels. The Gaussian kernel, which is the most important example. It is ISPD on every Euclidean space. Also the Laplacian kernel, which is again ISPD on every Euclidean space. The ESCA kernel, which is a very interesting family of positive definite kernels because they are compactly supported, and because of that, it's only positive definite on some Euclidean spaces. Also the multiquadrics, which is a ISPD kernels for when this exponent is negative, but is CND characteristic when this exponent is between 0 and 1. Another examples is the distance kernel on Euclidean space, proved by Zekeli in Rizzo in 2004. So you defined as the distance, the Euclidean distance between 2 points at the exponent alpha between 0 and 2, and it's always CND characteristic. There's another notation, the energy distance, but I'm using this CND characteristic because it provides us a general way to say this property. Also, the distance, the Geodesic distance on a real sphere, which is CND characteristic for alpha between 0 and 1. Alpha equals 1 is not CND characteristic, but is a conditionally negative definite kernel. This was proved by Gangoli on 1967. But he also proved that it's not, I'm sorry, he didn't prove it, but he also proved on the same article that projected spaces are, the geodesic distance on projected spaces are not metrics of negative type, which include the real, the complex, and the quaternionic projected spaces. But the distance on a sphere is CND characteristic for alpha between 0 and 1. Also, the distance on the hyperbolic space, real hyperbolic space, is CND characteristic for alpha equals 1. So hyperbolic space is a space of strong negative type, as well as the Euclidean space. And again, also is CND characteristic for alpha between 0 and 1. This was proved by Lyon in 2014. So from now on, I will talk about the examples of characteristic ISPD kernels based on completely monotone functions. Let me go back to the examples. Basically, all those examples, and actually most of the examples that we can find about characteristic and ISPD kernels rely either on some sort of harmonic analysis or on a set X or some very specific geometric property on a set X. But how can I provide examples of those kernels? More examples. Well, let's go back to a theorem proved a long time ago by Schoenberger in 1938. There is no need for topology in this context, but it says that you have a kernel, gamma is CND, if and only if this kernel, e to the minus sigma gamma, where it's positive definite for every positive sigma. So what we proved based on this theorem, using a LP version of the Stone-Weierstrass theorem, proven in Farrell in 62. So just to recall, the Stone-Weierstrass theorem the initial way that it was proved is that for every compact space on Euclidean, every compact subset of the Euclidean space, the space of polynomials restricted to this compact set is dense on the Banach space of continuous functions defined on this compact set. So, well, polynomials approximate every continuous function in interval 0 to 1. It's an example. There are several versions and extensions of this theorem. The one that we use is a LP version using by integrable functions, proving for Rao in 1962. And with this theorem, what we prove is the following. If you have gamma, a conditionally negative definite kernel with a bounded diagonal, the diagonal must be bounded because this kernel must be bounded. Then this kernel, E minus gamma, is ISPD if and only if those two sets are equal. Well, but what are those two sets? If you say that a kernel gamma where those two sets are equal are metrizable, what we have is that the kernel gamma is metrizable if and only if this kernel, the gamma, is a metric. Gamma being metrizable or not, the gamma will always be a pseudometric, which means there is a non-negative function and it's metric and it satisfies the triangle inequality. The only thing that we don't know is if the gamma xy equals to 0 if and only if x equals to y, which when satisfied, it means that those two sets are equal. So in other words, we can rephrase this theorem as gamma. If gamma is a continuous, then the kernel with bounded diagonal, this kernel is ISPD if and only if gamma is a metrizable kernel. In particular, if gamma is the distance on a metric space of negative type, then this kernel d gamma would be the square root of d, which well, is a metric. And then, for instance, the exponential of minus the distance on a Hilbert space or in real sphere on a Euro parabolic spaces, all of those kernels are integrably strictly positive definite. We can generalize this result by, again, using a theorem from Schoenberg from 1938, which describes the set of positive definite radial kernels on all Euclidean spaces or equivalently on all Hilbert spaces. So it describes which functions, continuous functions on interval 0 to infinity to real numbers, this kernel is positive definite. What it says is that a function with this property must be infinitely many times differentiable, and it must satisfy this equality, those inequalities, I'm sorry. A function with this property is called completely monotone function. Completely monotone function, they have equivalent integral representation, and with that integral representation, we have that kernel function f applied. This kernel must have this representation, where a is a non-negative number and lambda is a non-negative Borel measure on the interval 0 to infinity. And this representation is unique. So using this theorem from Schoenberg, what we prove it is that if you have a continuous completely monotone function, gamma, a continuous conditionally negative definite kernel with bounded diagonal, then this kernel f with applied gamma is ISPD if and only if the function f is not constant and gamma is metrizable. Well, the function f is not being constant. Let me come back. Because the representation is unique, is equivalent at saying that this measure lambda is not a zero measure. And well, gamma must also be metrizable. So some examples. The function f of t e to the minus t alpha, alpha between 0 and 1, but not including 0 because it would be the constant function. So for alpha equals 1 and gamma being the distance on a distance square on a Hilbert space, we reach that the Gaussian kernel on a Hilbert space is an ISPD kernel. If you pick alpha equals 1/2 and again gamma equals to this square distance on a Hilbert space, then we reach that the Laplace kernel is SPD on every Hilbert space. And another example of complete monotone function is the multiquadratic for the negative exponent. Now I'll talk about some examples about energy distance or CND characteristic kernels based on Bernstein functions. The idea is the same, and basically it's consequences of the fact that e to the minus gamma is an SPD kernel under some circumstances. So for that we use another theorem from Schoenberg, which describes the set of continuous functions where this kernel is CND for every Hilbert space. A function g with this property must be infinitely many times differentiable, but now this derivative must be a completely monotone function. And a function with this property are called Bernstein functions. Bernstein functions also have an integral representation, which then we can write g uniquely as this way, where a is a number, it's no restriction, b must be a non-negative number, and lambda is a non-negative Borel measure on interval 0 to infinity, not necessarily finite, but with this integral condition. One thing that is important to us is that b is a non-negative number, this is a non-negative function, this is a non-negative function, and this is a non-negative measure. This we use it. This is a technical thing, but it's useful for our results. So what we proved is that if you have a continuous Bernstein function and gamma, a continuous conditionally negative definite metrizable kernel with a bounded diagonal, so the same conditions as the completely monotone case, this kernel g applied at gamma is a CND characteristic kernel when g is not a linear function, which means that this measure, because the representation is unique, it means that this measure lambda is not the zero measure. If g is a linear function, then the fact that its kernel is CND characteristic or not depends uniquely on the fact that if the kernel gamma is CND characteristic or not. Examples of Bernstein functions, g equals t to the alpha between 0 and 1, where if you pick again gamma as the square distance on the Hilbert space, you reach the energy distance kernel, which by this result is CND characteristic. Also, another example is the function g being equal to the logarithm of t plus 1 is also a Bernstein function. So as I mentioned before, the distance kernel on Euclidean space for this exponent alpha between 0 and 2 is a CND characteristic kernel. So what occurs if alpha is larger than 2? Well, alpha equals 2, if you apply the definition of the metric that when I define the CND characteristic kernel, I define a metric on the space of probabilities. That formula is basically describing the difference between the vector mean of the two probabilities. However, if alpha is between 2 and 4, the same type of double integral that I defined on that case, but I've changed the sign here, it still defines a metric on the space of probabilities with good integrable conditions with respect to the kernel. But in order to define a metric, those two probabilities must have the same vector mean. If alpha is in between 4 and 6, the same type of double integral, but now we must place the minus sign here. So it keeps changing. You can define a metric on the space of probabilities, but now they must have the same vector mean and the same covariance matrix, and so on. So now I'll talk about some examples of characteristic and ISPD kernels on our product spaces, again, as a consequence of the declaration of when a to the minus gamma is a characteristic, is an ISPD kernel. So if you have a gamma, a continuous, and again, same demetriable kernel with a bounded diagonal, but now I must assume two other properties. This ifemon, I must assume this ifemon in order that this kernel is a bounded kernel, because every characteristic, every ISPD kernel must be bounded. And also that gamma is a non-negative function because, well, I can't divide this by 0. So, and under those circumstances, this kernel is always an ISPD kernel. It's possible, the fact that this kernel is positive definite is known for a while, but it can be generalized. You can replace the exponential with a completely monotone function. And we also provide the same sort of analysis that replacing with using matrix kernels. So, and this context, we don't need this 1 divided by gamma, but this exponent m here. So the class of kernels is a bit different. This type of kernels are very interesting. Well, for instance, if you use X as the two-dimensional sphere, they're used on tree statistics. And also these kernels, if you fix U and V, it's always a Gaussian kernel. So it's a very interesting family of positive definite kernels. Now I'll talk about characteristic and ISPD kernels on real hyperbolic spaces. Oh, there's a question. Is there any general theory behind the distance behind from x to the minus y? It's related to what is the name? Positive definite kernels on Euclidean spaces with I'm sorry, I forget the name, but there is a whole theory where this kernel is an example. So basically, let me rephrase it. Conditional negative definite kernels have a restriction. The sum of the coefficients must be 0. Alpha between 2 and 4, you must have another restriction that polynomials with order 1 must also be 0. Alpha between 4 and 6, polynomials with degree 2 must be 0. There is a name for this type of kernels, but unfortunately I forgot the name. I can provide you a reference for this. Oops. So some examples of characteristic and ISPD kernels on real hyperbolic spaces. So just to remind, what is a real hyperbolic space is the set of points on a Euclidean space that satisfies this polynomial equation, but the last variable must always be positive. And I use the Poincare half-plane model just because it simplifies some of those equations, but any other model will reach the same results. Just the formulas will be a bit different. On the hyperbolic space, we define the brackets function, which is a very important function for us because it satisfies the following property. So the hyperbolic cosine of the distance, the geodesic distance between 2 points, is equal to the brackets functions on those 2 points. This formula is very similar to the one on the real sphere. As you may know, the cosine of the geodesic distance between 2 points on the sphere is equal to the inner product of those 2 points. So it's the same relation, but it's just replace it, the cosine with the hyperbolic cosine and the inner product with the brackets function. Well, the same relation occurs on a generalized hyperbolic space where we replace the finite dimensional Euclidean space with any Hilbert space. I'm sorry, it must be a real Hilbert space. And the brackets function and the relationship between the distance and the brackets function, it works on the same way. So Fajot and Herzala in 1974, but it can also be found on Christian Beck books about positive affinity kernels. They wanted to characterize what are the positive definite radial kernels on a real hyperbolic space, on every real hyperbolic spaces. The characterization that they found is this one, but because similar to the real spheres, we have positive definite kernels on real spheres that are defined by the distance, but also defined by the inner product. And those two are in some sense equivalent because you can go from one to the another using the cosine and its inverse. The same thing occurs here, and using the brackets function, you reach this characterization, or equivalently, that this function g, the exponential, must be a completely monotone function. Or in terms of the radial kernel, what we get is this representation here using the hyperbolic secant. And actually, this representation is very similar to what we have on the Euclidean case, which is a function at the exponent r, but in that case is the Gaussian kernel, e to the minus the distance between x and y squared. So what we proved, again, using the fact that e to the minus gamma is, under some conditions, is an ISPD kernel. What we proved is that this kernel is always ISPD for every positive number r. And in particular, every one of those, let me come back. Every one of those kernels are ISPD, at the exception if lambda is the direct measure on the point 0, or equivalently if f is the constant function. Although I've write here the finite dimensional real hyperbolic space, but actually it's every real hyperbolic space. This function, this kernel, will always be ISPD at the exception, I'm sorry, if f is the constant function. Just to conclude this talk, it is part of the proof of Fajot and Zala, and also on the Beck's book, to prove those results about the real hyperbolic space, that the brackets function is a conditionally negative definite kernel. Also, the logarithm is a almost Bertin function. It's not continuous on 0, but it's sufficiently good so that we can prove that the logarithm of the brackets function is a CND kernel. If we use this very strange formula, it's almost a Lohan type of approximation of the first of the hyperbolic cosine. In particular, the distance on a generalized any dimension real hyperbolic space is by definition the inverse of the hyperbolic cosine of the brackets function, because of that relation between the hyperbolic cosine of the distance equal to the brackets function. It's just reverse this relation, and then using this representation is equal to the logarithm of the brackets function and this. But as I mentioned before, the logarithm of the brackets function is a CND kernel. Those kernels here are ISPD. So with the minus, there are all CND characteristic. And if you sum CND characteristic kernels, and if you sum CND kernels, in the end you also get a CND characteristic kernel. So this distance is a CND characteristic kernel, which by definition means that the distance on a real hyperbolic space is a metric space of strong negative type. So those are my references. As I mentioned, my results are based on those two papers. everything that I mentioned about high-speed and characteristic kernels is based on this paper on Gaussian kernels on Hilbert spaces and kernels on hyperbolic spaces. Everything that I mentioned about CND characteristic kernels is contained on this paper that I submitted to arXiv today. That's why I don't have more details about it. It's called Generalization of the Energy Distance by Bernstein Functions. And well, thank you for your attention.
Okay, if there are no further questions, then we move on to Huang.
So hello everyone, my name is Huang, and today I will present a work with collaboration with my Hara-san. The title of my work is a function on graphs with Lovax vector. So this is the outline of my work for today. So let's start with an introduction of the problem that I'm targeting. So this is a graph learning problem, and more specifically, this is graph classification. So suppose we are given a set of graphs, and each of these vertices are associated with some kind of features or some like tagging, for example, saying the tag saying it is a carbon or hydrogen in molecule classification, for example. And given some training, let's say we have two training class here, we want to learn find a general hypothesis that separate these given graphs into two or more class. So there is many applications to this kind of general problem. For example, molecule classification. We can detect whether given molecules represented as a graph is toxic or not, or even more advanced is when given a molecules, we want to find the other two molecules that when react result in the given molecules. So that is one of the applications that I'm working on with my collaboration. Furthermore, there is social network classification task, which means we can look at the interaction between peoples in a network, and we can classify whether that type of interaction as a whole is interaction in computer science or interaction in like movies or some other communities. And another very closely related to self-driving car is point cloud classification, where the input are just discrete points, and we want to classify or we want to reconstruct sceneries using neural network. The existing approach usually use set neural network, but more recently, people find that by constructing a graph, for example, nearest neighbor graph, can help improving the accuracy of classification. So when we construct a graph from point cloud, graph neural network can be used to solve these kind of problems. So in general, there is a common approach, which is learning some mapping rule that maps from the graph structure and the features of each of the nodes or each of the vertices into some Euclidean vector or some vectors that is suitable for machine learning. So we can apply many different techniques of machine learning in downstream after we have this kind of mapping rule. So so one key property of this kind of mapping rule is that it has to be invariant or equivariant to graph isomorphism. So different from, let's say, convolutional neural network, where the convolutional kernels maps an image into some representation, some hidden representation. In those applications, an image doesn't, an image will change after a certain like permutation of the pixels. Of course, flipping or stretching will not change the topic of the image, but if we shuffle the pixels, then the image might change its meaning. However, in graph, we want to preserve the representation, the hidden representation under graph isomorphism, because otherwise it would be impossible to learn a meaningful representation of graphs. So around 2000 and before that, the existing work usually construct this kind of mapping rule based on counting or graph distance. So for example, subgraph kernels or Weyfisler-Lehmann kernels are very popular choice for mapping a given graph into some sort of vectors. For example, in bioinformatics, they have a concept of graph fingerprint where they can count substructure and matching substructure of a given molecules and then output along numerical vectors as a representation of that molecules. And in this line of research, in this line of approach, usually this kind of mapping is invariant by definition. So because it's based on counting. More recently, around 2010, 2009, starting from 2009, people have started to propose a special type of neural networks that work on graph structure. And a general idea for this kind of network is based on message passing, meaning each of the nodes will pass its own information to the neighbors and also gather information from the neighbors. And this has started in a really large literature of work. For example, there's a model named Graph Isomorphism Network in ICLR 2019, which connect graph neural networks with a Weyfisler-Lehmann algorithm. And there is some other approach, more practical approach like GraphSage for scalability, or representatively like Splice CNN, using graph spectral theory to applied in computer vision. So in this line of work, the key property of rho, it is invariant by summation of feature aggregation. So basically, after multiple steps of message passing, usually this graph neural network will sum up all the features found in all the nodes to find a final representation of a graph. So in our work, we study graph homomorphism count vectors as the mapping rho here. So let me give an example about what is graph homomorphism. So let's say we given a graph F and we have some target graph G. So G is something we want to learn about, and graph F here is something we can think of as a hyperparameters or as some fixed pattern that we want to match. So a graph homomorphism is a structure preserving maps, meaning, for example, this one is called a homomorphism. So we can map F2 to G2, F1 to G1, and F3 to G3. So as you can see in here, the connectivity between F1 and F2 is preserved by G1, G2. And similarly for F1 and F3 is preserved by G1 and G3, as I write down in this table here. And then when, let's say we keep mapping G1 to F1, then we have 6 other permutation of this mapping. So there is 6 in totals of different mappings that map following this particular pattern. And so another way of mapping is that if we keep mapping F1 to G1, but we map both F2 and F3 to G2, as you can see here, the structure, so the connectivity of graph F here is still preserved because F1 and F2 is preserved by G1, G2, and F1, F3 is preserved by G1, G2. So it is preserved. And this kind of pattern resulted in 3 mappings. Another way is we can map F2 and F3 to G1, and then we can map F1 to G2, G3, and G4. The connectivity of F is still preserved by this mapping on graph G. So we have another 3. So in total, there is 12 units of such mapping, 12 of such mappings. And yeah, this mapping, the size of this, the number of mappings, we denoted as home from F to G. And in this particular example, it is 12. And I would like to point out that the first group here is coincide with isomorphism. So in this picture, I hope we can see the difference between homomorphism and isomorphism. So graph isomorphism, subgraph isomorphism required a bijective requirement, meaning each of these vertices has to map uniquely onto another vertices, and it also have to be inversible. So the non edge has also to be preserved. So coincidentally, this first group here is also isomorphism, but graph homomorphism include the two other way of mapping down here. And this is also why graph homomorphism in our case here is much easier to count than subgraph isomorphism. So the formulas for homomorphism can be written down quite simply. So the first summation is summing all possible mapping from vertices of F to vertices of G. And then the next terms in here, the terms inside the summation, is basically just checking whether all connectivity of F is preserved in G. So that is a very, very simple formulation. And yeah, so each of these product return 1 for each valid mappings. So given some set of graph F, so F, the curvy F here is a set of small patterns, then the graph embedding can be defined as a stacking of different homomorphism numbers, starting from small f to g. So we can just keep inventing some kind of patterns that we want, and we stack them into a longer vector. So these vectors are also known as the Lovács vectors, studied by Laszlo Lovács, and usually in the literature, in the homomorphism literature, these vectors, this set F consists of all non-isomorphic graph up to size of graph G. But in here, we consider a much more restricted version of that for practical use. Okay, so the next session is I will discuss about the universality result. So first of all, I would like to discuss like why do we look at graph homomorphism. So the first motivation is from a very landmark theorem from Laszlo Lovács. So this theorem said that the two graph G1 and G2 can be identified, the isomorphism type of them can be identified from the homomorphism vectors. So meaning G1 and G2 isomorphic if and only if they have exactly same number of homomorphism for all simple graph F. So this is a very impressive result. We know that if F is some subgraph isomorphism counting, then obviously G1 and G2 are isomorphic if and only if they have the same subgraph isomorphism count. But for homomorphism, very interestingly, it's also the same result also holds. So that is the first motivation of our work, because now we see that okay, the Lovács vector can represent the graph uniquely up to its isomorphism. So, and then because the homomorphism vectors can represent the graph uniquely, we can think of building universal functions, so isomorphism invariant functions on graph G from the homomorphism vector. And because it is from the homomorphism vectors, it is much more suitable for machine learning tasks. And since we are talking about universality, there is existing universal approximator for graph function. And usually these work require very, very high dimensionality in computation. So for example, the figure A here represents a tensorized neural network. And usually the dimension of this graph is super exponential. So n to power of 4, for example, in order to build a tensorized graph neural network that is universal for all graph function. The reason why they need like super exponential is because the tensorized graph neural network has to be able to capture all permutation of the graph. And so in here, we can see that the tensorized graph neural network can totally implement the homomorphism number because it's very powerful. It can implement a homomorphism number. So if the homomorphism numbers is enough for us to build a universal graph classifier or a graph function approximator, then if we can prove that, then effectively we can prove this type of tensorized graph neural network is universal as well. So that is one reduction step into a more simpler model. But if the simpler model has a universality property, then the more complex one will also have that. So this idea results in a very simple proof for graph universality. Universality of tensorized graph neural network. So in here, we would also want to note that the homomorphism vectors also exhibit like high dimensionality, because if we set the graph the set of small graph f into size, into like arbitrarily large size, then the number of non-isomorphic graph up to size 14 is already a really large number, and we actually don't have a closed form formulas to enumerate all the non-isomorphic graph up to some size beyond 21, if I'm not wrong. So this result doesn't mean that we need less dimensionality. This result also require high dimensionality, but in a much more fine-grained way. So let's take a look at an example. For example, the Gene paper graph isomorphism network paper proved that one-dimensional wave phase Lehman test is implementable, but it is implementable by the graph isomorphism network, but it's required to some order of number of vertices of the graph in interest as a feature dimension. Another line of work by Maroon and Caravan. So Maroon and collaborator work on set neural networks, and then recently they also have lots of good papers on graph neural networks. And Caravans, usually these teams propose models that have very high tensor order. So for example, like Caravan papers, Caravan's model required tensorization in the order of n to power the n of power 4, which is very large. And in order to increase the representation power of this kind of model, we have to go at n to power of n step. So the step, each of the increase in the tensorization usually kind of really large. So in using homomorphism, our good news is that we have a set of small graph f to parameterize. So the more we add pattern graph into f, the more expressive our model can become. But it is not like in tensorization order more expressive, but it can be very fine-grained as we add more and more pattern into it. So, and then another good news is some class of pattern graph can be computed very efficiently. So this class is called tree width bounded graph, and the homomorphism can be computed in polynomial time. And so yeah, so as I said, restricting the set F, so without letting it to be all non-isomorphic graph. For example, if we restrict it into cycles, then we can discuss about different class of universal approximator. So let's start. So in here we borrow a definition of F invariant. So if a function f that sends a graph in a graph space G to some real number is F invariant, meaning any functions f will have the same values for G1 and G2 as long as the homomorphism from F to G1 is the same as the homomorphism from F to G2. So this one is F indistinguishable. So basically, even if these two graphs are different, we cannot distinguish them with the set F that we parameterize. So there are some concrete example. For example, if the set F is just a single vertex, so it's a singleton, then the graph that is not that is indistinguishable are graph with the same number of vertices. So if we have like a data set, all graph have the same number of vertices, then this set is obviously not a good choice because it is indistinguishable by just counting the number of vertices. And similarly, we can have an edge, and the homomorphism from F to G just basically counts the number of edges in the target graph. More involved, we can have in a more involved manners. For example, if we have a families of stars, then the set of graph that is indistinguishable is graph with the same degree sequence. So now our function can be much more expressive. It is restricted that if it has the same degree sequence, we cannot distinguish them, but otherwise it is okay. And another example is when set F consists of cycles. So cycle of psi3, psi4, psi5, then the F indistinguishable are all graphs with the same spectrum, which is quite a good classifier already. And so very exciting result recently by the group, Groher group, by Dell and in the Groher group. That is, if F are all graph of K of tree width bounded by K, then the F indistinguishable is graph that cannot be distinguished by K-dimensional wave phase Riemann test. So for featureless, so yeah, this is in this slide we talk about the main result of our work recently. That is, if F is any F invariant function as discussed before, then there exists a degree n polynomial that arbitrarily approximates the function F based on the homomorphism number. And similarly for, so theorem 3 is for unbounded graph because as soon as the graph is bounded, sorry, theorem 3 is for bounded graph because as soon as the size of the test graph is bounded, we have compact Hausdorff for free. But for unbounded graph, then we have to borrow notion. So first of all, we have to require function F to be continuous, and then we have to borrow the notion of compact Hausdorff of graph form. So in this case, in order to prove theorem 3, we have to assume G comes from a continuous graph form. So there is a bit of technical here for unbounded graph. But in practice, usually we can assume that the set of graph in our data set is bounded. And the remaining task is basically to check whether the condition of the Stone-Weierstrass theorem satisfies. And that is the main idea to prove these two results. So to verify some of the result we have, we run experiments. So for example, here are the synthetic graph experiments. CSL is a circular skip link. So these are 10 graphs. Actually, there's only 10 graphs in this data set. But for each graph, we generate 15 others that are permutated. So the vertices are permutated. So then we have 150 graphs and 10 class. So that is a classification problem. We have 150 and we have 10 class to classify. And the circular skip link data set has the exactly same degree sequence for all the graphs. So although they are not isomorphic, they have the same degree sequence. And the results show that, yeah, recent model, even like very, very recently proposed neural tangent kernel, cannot distinguish this data set at all, because obviously, GIN or GNTK are based on three pattern. So basically, one-dimensional. The most they can do is one-dimensional wave-phase Riemann. So it is, as expected, they perform very poorly on this data set. Another theoretical model is named ring GNN. However, the result for this model varies based on initialization a lot, and the author usually report the minimum and the maximum accuracy for this particular data set. However, for example, like in our work, we can just set the set F into cycles, and we immediately get the result because the set of cycles can distinguish the graph with the same degree sequence as long as they have different spectrum. And indeed, this graph has different spectrum. And similarly, for example, bipartite graph distinguish between random bipartite graph and random Arrow's-Rényi graph. We have similar result for graph homomorphism cycles. So, and then the last one is a very strong regular graph. So these are very, very strongly regular graph, and they are also co-spectral. So in here, if we use a brute force isomorphism check, we can distinguish the graph in Paulus 25 dataset. However, if we don't, then all existing methods, including our current isomorphism, homomorphism count, couldn't distinguish between these models. And thus far, I still couldn't find the pattern of F that can crack this particular data set yet. Okay, so that is a synthetic result. We also verify our result, our models on real-world data set. So these are example of the 3 data set we run more on in our papers. So if you are interested, you can check our papers. So the conclusion is in here is, of course, our paper, our method does not perform the best as in like the state-of-the-art performance within like 2 or 3% accuracy. However, first of all, it runs very, very quickly in terms of runtime, and there is not many hyperparameters to tune. And I think this could be a very good candidate to run as a benchmark or as an initial benchmark for graph classification models. And more importantly, because we have some kind of like subgraph counting, we can look at which kind of substructure is important for each of the data sets. So for example, for the 3 data set I show here, there is single vertex, edge, and triangle are the most important features to look at, to classify these models. To give a little bit of perspective, the dataset MUTAG is a mutagen dataset, so it is a chemicals classification problems where the graphs are molecules with size around 15 to 30 nodes. IMDb binary and IMDb multiple are a binary classification and multi-label classification of social network. So in conclusion, I would like to discuss a little bit of the big pictures of graph neural network recently. So I feel like graph neural network recently start to converge, like the direction of the community start to converge back into graph canonization many years ago. So the majority mask of the work are usually wave-phase Riemann based algorithms. So we have message passing and feature propagation, k-dimensional wave-phase Riemann, or most recently sparse wave-phase Riemann. And so basically most of the work is based on wave-phase Riemann algorithm. And our work lies in the homomorphism discussion of these based on the homomorphism approach. And recently in ICLR 2020, there is a paper that proves the first order logic with counting quantifier restricted to 2 variables. So graph neural network can implement any first or any statement in FOC2. So that is draw a connection between graph neural network and first order logic. However, there is an open question that remains, that is whether graph neural network is exactly exactly characterized by FOC2. And that is an open question for now. Because there is with Feisler-Lehmann homomorphism and first order logic, I found that there is another component, another view is EF game. So these four things actually closely connected. For example, like in our work, we use the result of Dell saying that the homomorphism actually connected to k-dimensional wave Feisler-Lehmann. And then first order logic is also connected to wave Feisler-Lehmann and graph neural network. Then there is, so basically in here, I'm trying to say here is there is four views of the same thing. And the majority of the work is based on wave Feisler-Lehmann. And there is many other room for homomorphism or first order logic or even EF game argument. And one of the things I think about the open problem in FOC2 implies GNN. So the open problem is that whether FOC2 exactly characterize GNN. And with argument from EF game, our conjecture right for now is that the answer is in the negative. So there is many things to do in graph neural network beside the majority. There is a popular work in wave Feisler-Lehmann based models. So in this work, we have demonstrated graph homomorphism is a very interesting object to study in graph classification, and it's quite practical as well. And so in the future, we are continuing to study about the generalization to other graph method based on homomorphism, or developing learning theory for graph based on homomorphism density. Because there's a very deep lemma from Lovax that says the larger the graph in F, the more sensitive to of the homomorphism numbers. So that sensitivity is very important in learning, because the generalization and sensitivity are actually in a trade-off. So there is a large potential to develop learning theory, a new learning theory for graphs based on the homomorphism density. So that is the end of my talk, and thank you very much for listening. If you want to play around with the graph homomorphism, you can check out the repository I have here, and here is a manuscript, and yeah, please email me if you want. And I'm happy to take questions. Yeah, thank you very much for listening.
That's the question, Huang, Q&A.
Oh, okay.
Question.
Okay. Okay. So the question is, for tensorized G and N, could you explain more about its key concept and benefits? Yes. So, yes. So for tensorized graph neural network, in here, the key concept, why they propose this, is because they want to build a truly universal approximator. So for non-tensorized graph neural network, it is limited by what wave Feisler-Lehmann and one-dimensional wave Feisler-Lehmann algorithm can do. So for tensorized graph neural network, they want to go beyond that constraint. So basically, that is the main key concept that I can think of right now. That is, they tensorize the graph neural network in order to capture all permutation of the adjacency matrix, so to speak. And because they can capture all the permutations, they can argue that this kind of construction is universal, that it can approximate any function defined on the graph. Yeah. However, like, it is not very practical, because as you can see, the implementation require O to power of n to power of n to power of 4. So I think in here the benefits are stopped at like theoretical benefits. There is another improvement. So the recent improvement that I put so in here is called sparse wave phase-Riemann. So it is a higher order wave phase-Riemann, which is kind of corresponding to higher order tensor GNN. But instead of going OK, they pick like at which tuples are selected instead of like forcing all the tuple to be K. They can have like K-1, K-2 tuples. So that is another point about tensorized GNN. And yeah, I hope that answers your question.
Yeah, thank you for your answer. So
yeah. Yes.
I'm TB.
Oh yeah.
So,
yeah,
it seems that the expressive power is increased. I'm wondering the performance, generalization performance, how is it?
So in here, the generalization performance actually not as good. I mean that I haven't run this experiment exactly because of the high tensor order, but in this line of work, we only discuss about expressivity instead of generalization. So the one thing you can observe is the more expressive, the less generalization. It could be without regularization. So yeah, so I can only draw that conclusion from like the work from, for example, k-dimensional wave phase-Riemann usually don't have as good performance as one-dimensional wave phase-Riemann. So that's why I say the generalization result might not be as good when we make it more expressive.
Okay, thank you. Thank you very much.
Thank you for your question.
Are there other questions for Huang? Okay. If not, then thank you for the presentation. Thank you
thank you very much.
So thank you very much for joining us. And this is the end of our seminars. So please come back and join us next week and the subsequent weeks for the other seminars. The next week will be by the knowledge acquisition team. So thank you very much and have a nice day.